Started the organization of the nervous system. We focus on synapse, different properties of the synapse, and then we continued with receptors and neural networks. We have seen different principles that govern the function of receptors. And after that, we started the sensory system by focusing on tactile sensations, right? Proprioception and also vibration. And I explained about different receptors, different pathways, ECML, anterolateral system, and so on, and the function of the cortex for understanding touch, vibration, and pressure, right? And I provided you with 3 different files, one for pain and temperature, another one for spinal cord reflexes, and the last one was about the motor cortex and brainstem. And today we will continue with the cerebellum. So actually, I suppose that you are now familiar with spinal reflexes, motor cortex, and brainstem pathways, right? I mean, pathways that originate from the brainstem. Okay, so cerebellum is a side loop for the motor system. So, if you stimulate this area of the brain, nothing happens. Okay, so it's in sharp contradiction with motor cortex. If you stimulate primary motor cortex electrically, you can see a twitch of a muscle in the body. For example, if you put it in the hand area of the motor cortex and stimulate the area, you will see a twitch-like movement in the hand, right? In the opposite side. If you stimulate the right side, you will see movement on the left side, right? And stimulation of supplementary motor area or premotor area needs higher level excitation. I mean, more electrical current to produce a movement. But in the cerebellum, stimulation doesn't cause any movement or any sensation. So people believe that this is a silent area of the brain in the past. Okay? But if you remove the brain, the cerebellum, or if there is any damage to the cerebellum, then there will be severe deficits in motor coordination, especially for fast movements, for rapid movements, like playing piano, playing guitar, okay? Writing. So especially for fast movements, there will be uncoordination of movements. But there is no paralysis, no loss of sensation, no problem with understanding the nature of the task you are doing. Okay? So, based on this, they reached the conclusion that cerebellum influences movements by modifying the activity pattern of upper motor neuron. You remember from the video 5 that we have upper motor neuron, lower motor neuron. Lower motor neuron is the alpha motor neuron located in the anterior part of the cell of the spinal cord, but all other neurons located upward, meaning those that start from the cortex or from the brainstem and go descendingly through the spinal cord and reach the alpha motor neuron, all of them are called alpha, are called upper motor neuron. Okay? So, upper motor neuron is modified by the cerebellum. So cerebellum doesn't send any direct axon to alpha motor neuron or any axon to muscles. So it can change the activity of motor centers, other motor centers. So it can regulate timing of motor activities. Okay, so all of these are important for coordination of activity. Timing, progression from one movement to the next one, intensity of the contraction, and the interplay between the agonist and antagonist muscle. All of these are regulated by the cerebellum. So this way, the cerebellum can cause coordination of motor activity. So if there is damage, coordination is lost. Okay? So, how does the cerebellum do this? So, it receives two versions of information. The first is the motor command originated from the cortex. So it knows the desired movement that the motor system wants to do. Okay? The desired movements of the motor system. And it also receives sensory feedback information from the body. So it knows the current state of the muscles, joints, and the body generally, okay? So static position, dynamic position. Remember? Okay? So it can compare the command, motor command, and the sensory feedback. If they match each other, then there is no problem, okay? Okay, everything is good. If there is mismatch between these two versions of information, then the cerebellum sends corrective signals to the motor system. So motor system can correct itself. Okay? So we compare the actual movement, sensory feedback. With the intended movement, motor contact. Sends corrective signals back to the motor system. These signals are very fast, so they are instantaneous, and subconscious, so you're not aware of this, right? So this way they can increase or decrease the level of activation of specific muscles. So, it's also important for helping the cerebral cortex in planning and programming the motor movements, right? Especially for sequential movements. Which area of the brain is important for sequential movement?
For? Good area is important for?
Sequential movement, so you know that we have several areas in the brain for voluntary movements. Primary motor, supplementary motor, premotor. One of these is very important for sequential movements.
Primary motor?
Primary, no. Primary is mainly important for execution or for performing an action. So performance is coordinated and organized by primary motor. You have supplementary motor area, which is important for sequential movement. So when our movement is composed of several other movements, like turning the radio on, has several movements, reaching, pressing, turning, right? So this sequence of movements, this is only an example, okay? Movements like these are controlled by supplementary motor. So the sequence is programmed and planned by the supplementary motor area. Now, the cerebellum is also important for planning of sequential movements. So there should be an interplay between the supplementary motor area and the cerebellum for programming this type of movement. Okay? It's also important for learning. So you know that when we do the movement for the first time, there may be some mistakes with the movement, so it's not so precise. But after repeating the movement several times, and you repeat it on, then you will become more and more precise, right? So this is a type of learning, motor learning, and this learning depends on the setting. So, you know the anatomy of the cerebellum, you know that it has an anterior lobe, a posterior lobe, flocculonodular lobe, right? And in physiology, we have another type of view of the cerebellum. So we have vermis, we have intermediate zone in the cerebellar hemisphere, we have the lateral zone, and we have the flocculonodular, right? So flocculonodular lobe, vermis, intermediate zone or medial zone, lateral zone, right? So this is the anatomy of the cerebellum, and you know that each part of the cerebellum is connected with some deep nuclei inside the cerebellum. You know that means, right? So, the NPH nucleus is associated with the lateral zone of the cell. Interposed nucleus, which is composed of lobus is associated with the intermediate zone. And the vestigial nuclei that are related and connected to the valence part. What is the nucleus for florculonodular lobe? Do we have any nucleus, any nuclei for the florculonodular lobe? Vestibular nucleus. So it's functionally connected with the vestibular nucleus, but it's not located inside the cerebellum. Okay? All other areas have their specific nucleus inside the cerebellum, but this part doesn't have a nucleus inside. Okay? The nucleus is the vestibular nucleus located in the medulla pons. So, these parts are connected with different ends. Similar to motor cortex, that we have a map of body inside the motor cortex. Also in the cerebellum we have a map of body. So you can see that the map is located in the valgus and intermediate zone. We don't have any map of the body in the lateral zone. Right? So, and we have two maps. Superior one and posterior. Okay. So when we have a map, it means that this specific area, so any specific area of this map is associated with a specific part of the body. For example, here we have the left arm. Okay, so it's associated with the left arm of the body. So it receives sensory feedback from the left arm. But this part receives sensory feedback from the right arm. But it also receives information from the cortex. So you know that in the primary motor area, we have a hand area. On the right side of the brain, we have a hand area for the left hand, left arm, and on the right side, on the left side, we have an area for right arm, right? So the left arm also receives motor signals from the left arm area of the cortex. Okay? So it receives both sensory information and motor information. Motor information from the cortex, sensory information from the brain. But it also receives other type of motor information from other motor systems. So you know that in the brainstem we have reticular formation, important for movement, especially for postural movements. And you should know that we have also vestibular nuclei that are important for balance. Right? So they are also motor systems. We have red nucleus located in the leaf. And it's also important for movement, especially for hands and arms. Right? So these maps are also connected with these areas. I mean, so they are connected to the cortex, body, reticular formation, red nucleus, vestibular nuclei. So all motor systems provide input to these things. In the lateral zone, we don't have any map. Nothing. I mean, come here from the body or from a specific motor part of the brain. Okay, so let's focus more on the input to the cerebellum. You know that from the cortex, frontal and parietal cortex, we have corticopontine pathway. So they go to pontine nuclei. From pontine nuclei, they go to the cerebellum. So we have corticopontocerebellar tract. Right? So it originates from the motor part of the frontal lobe and sensory part of the parietal lobe. So this is the main pathway to the cerebellum, the biggest one. Right? We have also other inputs. So let's start from here. So we have input from vestibular nuclei to the cerebellum, vestibulocerebellar tract. Right? Reticulocerebellar tract, spinocerebellar tracts, several tracts, right? So, from the spinal cord, we have fibers that go to the cerebellum, from the reticular formation, and also from the vestibular. All of these areas also cortex and red nucleus, also provide input to the inferior nucleus. Right? And from here, we have inputs to the cerebellum, oligoid cerebellum. Right? So these are inputs. So I think that you know that from the anatomy, that cerebellum has vestibular cerebellum, right? Spinal cerebellum, cerebral cerebellum. So fibers that originate from the spinal cord go to the spinal cerebellum. Which part?
Can you repeat the question, please?
Yeah. Spinal fibers go to the cerebellum. They terminate in the spinal cerebellum. Which part of the cerebellum is spinal cerebellum? Lateral part? No.
No, near the vermis.
Yeah, vermis and intermediate, so both of them. So we call them spinal cerebellum. So fibers from the spinal cord go to the vermis and to the intermediate zone. Right? Fibers from the vestibular nuclei go to vestibular cerebellum. Which part is the vestibular cerebellum?
The lateral parts.
Lateral part, no.
Medial.
Medial part, no.
I don't.
So only one part remains.
Along the axis. On the central axis.
Central axis.
Like what's it called? Vermis, right? Like
No, the vermis is spinal cerebellum.
So vermis is part of the spinal cerebellum. But actually I'm now looking forward. Vestibular cerebellum. It's a flocculonodular lobe. Right? So, from the vestibular nuclei, fibers go to the floccular nodule. And you know that nodule is part of the vermis. Right? In the
Yeah,
middle
it's like-
side. Yeah, it's
comes from
very
the-
small. It's part of the vermis, but we collectively call flocculonodular lobe the area related to the vestibular nuclei. Okay? So, cerebral cerebellum. From here, they go to the pons. From the pons, they mainly go to the lateral side, lateral part of the cerebellum. We call that cerebral cerebellum. Okay. You can see also the fibers, but we will understand this. Let's go on. And let's focus more on the spinal input. Okay? So, fibers that originate from the spinal cord and go to the cerebellum start mainly from the Clark nucleus. Where is it? Clark nucleus?
Clark's nucleus is in the
Posterior.
intermedial medial part of the spinal cord.
Posterior.
And the posterior part.
Yeah, it's located in the posterior side of the
And the
dorsal
intermediate part
wall.
as well.
Yes.
Yeah, it's close to the layer 7 of the dorsal horn,
Yes.
right? And it is spread over C8 to L2 segments, right? It receives proprioceptive information from the lower part of the body,
Yes.
right? So lower part of the body sends its proprioceptive information to the Clark nucleus. What are the proprioceptive information? From which receptors they come?
Deep receptors.
Deep receptors. So, can you call them? Which receptors exactly?
No, not necessarily. Mechanoreceptors.
So, they are all mechanoreceptors.
Oh.
Yeah. So, muscle spindle, Golgi tendon receptors, joint receptors,
Yeah,
maybe
yeah.
Ruffinians,
Yeah.
right? And some of the tactile skin receptors.
Yeah.
Right? So, from muscle and joint receptors, information goes to Clark nucleus. Clark nucleus is the origin of the dorsal spinal cerebellar tract. They go to the cerebellum through the inferior cerebellar pylon. Right? But We have also ventral spinal cerebellar tract. This. The type of information that is conveyed in this pathway is not sensory. It's mainly motor. It originates from the anterior horn. Right? And anterior horn neurons receive information from corticospinal, rubrospinal tract, and also internal pattern generators. So these pattern generators are neurons that are important for organizing movements like walking. So it's a pattern. Okay? Yeah. So neurons related to walking, neurons that originate from the red nucleus, neurons that originate from the motor cortex come here in the anterior horn. They terminate on alpha motor neurons and also interneuron here. And from these neurons, we have some signals that go through the ventral spinal cerebellar tract to the cerebellum. So we call this type of information efference copy of the motor command. So motor command comes from the cortex to the spinal cord. One version of this goes back to the cerebellum. Right? So, what about the upper part of the body? So this one was for lower part. Do you remember from your anatomy? Proprioceptive information from arms go to each nucleus in the brainstem. Each nucleus in the brainstem receives proprioceptive information.
With nucleus?
Yeah.
Ambulus?
Ambiguous? No. External cunate or accessory cunate nucleus. Accessory cunate nucleus receives proprioceptive information from upper part of the body, from arms. So, we have proprioceptive information from Clark nucleus related to the lower part of the body. We have proprioceptive information from upper part of the body in the accessory cunate nucleus, and from here we have cerebellar tract. Okay? But there are also other spinal cerebellar tracts. I mean, other information from the spinal cord to the cerebellum. They go to the dorsal column nuclei, no, gracilan, right? Spinal reticular pathway, spinal oligoid pathway. So from the spinal cord, they go to dorsal column nuclei, reticular formation, oligoid nucleus, and from here they go to the cell. Which part of the cerebellum? Spinal cell. Which is composed of vermis and intermediate. So these are neuroanatomy, right? You should know the connections. Okay. So now let's focus on output. Okay, output from the cerebellum to motor systems. So from vestibular cerebellum to from vestibular cerebellum, output goes to vestibular nuclei, right? Lateral medial. Lateral vestibular nucleus, medial vestibular nucleus. They are important for balance and eye movements. So this part is important for balance and eye movement. From vermis and from intermediate zone, spinal cerebellum, information go to medial and lateral descending systems. And they are involved in motor performance, motor execution. What are these systems? Medial descending and lateral descending system. Can you name them?
The tracts, you mean?
Yes,
Those tracts?
Yes. Rubrospinal is lateral or medial?
Rubrospinal is lateral.
Lateral. What else?
Corticospinal.
Rubrospinal has two parts, lateral, ventral.
Lateral.
Which one is lateral? So lateral corticospinal tract is part of the lateral descending system. What else?
Vestibular.
Vestibular.
It's medial.
spinal tract.
Take to slow down.
It's medial.
Mm.
Take to spinal tract. Medial. We have two reticular two reticular spinal tracts. One originates from one area, the other one originates from another area. So, reticular, what? Spinal has two parts. One that originates from pons. We call this pontine reticular spinal. Another one from medulla. Medullary reticular spinal. Pontine is excitatory. Medullary is inhibitory. So this one activates axial musculature. This one inhibits axial muscles. So we call them anti-gravity muscles, right? So anti-gravity muscles are excited by pontine reticular spinal tract or inhibited by medullary reticular spinal. And there is always a balance between these two, so we can fit our posture, our desired posture. So standing or sitting or lying, okay? So this is determined by this. So rubrospinal, lateral corticospinal or lateral descent. All other pathways are medial descending pathways. So they are under the control of intermediate zone and vermis. Vermis for medial, intermediate zone for lateral. And the lateral hemisphere, the lateral side of the hemisphere sends the information to the cortex, motor and premotor cortex, and they are important for motor planning. So you should remember these four expressions. Balance and eye movements is related to vestibular cerebellum or floccular. Motor execution.
Related to the lateral parts. Oh wait, sorry, the intermediate and the vermis.
Vermis, very good. Motor programming or planning.
Lateral.
Lateral. Good. So now let's see more details in this general scheme. So let's focus on vestibular cerebellum, which regulates balance and eye movement. So you know that vestibular cerebellum has two parts: nodulus, flocculus. Nodulus is part of the vermis, and we have flocculus, right? Nodulus is mainly involved in balance. Flocculus is mainly involved in eye movement. Okay? So, from the nodulus, fibers go to lateral vestibular nucleus, which is the origin of lateral vestibular spinal tract. It excites axial muscles and limb extensors. So extensors of limbs, right? So, and axial muscles. So they are activated by this pathway. They cause balance. When? During the stance or during the gait. So any damage in this part may disturb balance of the patient. Right? So the patient cannot keep the balance during walking. So they tend to put their leg like this in order to keep their balance. Right? Okay. Lateral vestibular cerebellum, flocculus. Fibers go to medial vestibular nucleus. That one was lateral. Okay? Medial vestibular spinal tract. So you know that it goes down to cervical and mid-thoracic level. That's important for eye movement and neck movement. Okay? So, it controls movements of eyes and coordinates movements of the head and eyes. So whenever eyes go this way, head also goes this way. Okay? So lateral vestibular cerebellum. Lesions here causes deficits in smooth pursuit eye movements. Smooth pursuit eye movements. Imagine that you are watching or looking at a fly that is actually flying in the air. So So you follow the insect, okay, by your eyes. So this is called smooth pursuit eye movement. Okay? Any damage in this part actually interrupts smooth pursuit eye movements. Awareness also is important for smooth pursuit eye movement. So awareness shares some responsibility for smooth pursuit eye movements with philologists. The next part, spinal cerebellum, has two components. Awareness intermediate. Awareness that controls medial descending pathways, intermediate zone that controls lateral descending pathways, right? So you know the general. So from awareness, cortex of the cerebellum. Fibers go to the fastigial nucleus, deep nucleus, right? From here, fibers go to reticular formation and lateral vestibular nucleus. So the origin of two pathways. Reticular spinal tract, vestibular spinal tract. They go to the neck, trunk, proximal part of the arms. So they are important for both balance and posture. Mainly posture. Okay? But they are also involved in balance. So you can see also the figure, okay? So from bearings, some fibers go to reticular formation, so reticular spinal tract, they go to axial musculature. But some other fibers go to paths. Let's see. From intermediate zone, we have input to interposed nuclei. From the interposed, we have two pathways. One goes to the magnocellular part of the red nucleus, which is the origin of the rubrospinal tract. The other one from interposed go to the thalamus, ventrolateral, ventral anterior. They go to the cerebellum, to the cerebral cortex, made in the primary, which is the origin of the corticospinal. So two pathways, rubrospinal, corticospinal, are connected with the intermediate zone of the spine, of that cerebellum. So spinal cerebellum has two parts, vermis, intermediate zone. Vermis controls medial descending pathways like lateral vestibular tract and reticular formation, okay? But intermediate zone mainly control rubrospinal tract and corticospinal tract. These two are important for limb movements, but medial systems are mainly important for balance and posture. Got it? So, lesion in the intermediate zone may cause disruption of ipsilateral limb movements. Okay, the last one, the last part of the cerebellum. Cerebellum is important for planning and programming of movements, especially for sequential movements. So from lateral zone, fibers go to dendrite nucleus. From here, they go to thalamus. From thalamus, they go to premotor, primary motor, and association areas of motor sensory function. Urban area 5 and 7, remember? Okay? So, you know that these areas are important for planning. So they help planning of movements. Another part, another pathway is pathway from dendritic nucleus to parvocellular part of the red nucleus. They go to the inferior oligonucleus, oligocerebellar tract, cerebellum. The first one is important for sequential motor activities. Damage causes incoordination of complex purposeful movements. Right? Second one is important for motor learning. I will talk about that. Okay? Motor learning. So red nucleus has two parts. Okay? Red nucleus. superior part, inferior part. Superior part is called parvocellular. Inferior part is called magnocellular. Parvo means small cell. Magno means large cells. Magnocellular part is the origin of spinal joint. Okay? But parvocellular is not origin of any tract. So it goes to oligoid nucleus. From here, they go to cerebellum. So parvocellular part is important for motor learning. This one is for controlling distal part of the limbs, right? Okay. Anything is clear?
Yes.
Okay. Easy and simple. So you call this easy peasy. So, now let's see the physiology. Okay? So far we talked about anatomy. Now let's talk about physiology. How the neurons in the cerebellum can generate the general function of the cell. Okay, you know that we have cortex in the cerebellum and deep nuclei. Right? Cortex has 3 layers. Molecular layer, Purkinje cell layer, granule cell layer. So in the molecular layer we have dendrites. You can see dendrites. In Purkinje cell layer we have the soma of Purkinje cells. And in granule cell layer we have mainly granule cells. But we have also Golgi cells. No, Golgi cells. Basket cells and slate cells are in the molecular layer. Okay? So here you can see physiological connection between neurons. Okay, so let's review the inputs. I told you that input to the cerebellum are from cortex. Let's go to pons, from pons to the cell. From the spinal cord, different pathways, right? Reticular formation, vestibular nuclei, so all of them go to the cerebellum. Fibers that originate from these areas and go to the cerebellum are called mossy fibers. Mossy fibers. Mossy fibers, yeah. But we have another input to the cerebellum, but that originates from oligoid nucleus, inferior oligoid nucleus. Fibers that originate from inferior oligoid nucleus are called climbing fibers. So,
Is this one green?
yeah, this one. From inferior olive, we have climbing fibers. All other inputs are the original mossy fibers. So, both mossy fibers and climbing fibers send some collaterals to the deep cerebellum nuclei. Okay, so this is the Purkinje cell. This one is the deep cerebellar nucleus. There is a connection between the Purkinje cell and the cerebellum. So this connection is very good, right? So mossy fibers and climbing fibers enter the cerebellum. At first, they send collaterals to the deep cerebellar nuclei. Then they continue their axon upward. Okay? Climbing fibers go directly to the molecular layer and make several synapses with the dendrites of the Purkinje cell. But mossy fibers first go to the granule cell layer, make connection with granule cells, then granule cells send axons to the molecular layer. In the molecular layer, they divide their axon into 2 branches that are located horizontally. Okay, we call them parallel fibers. Parallel fibers. They also make synapses with the dendrites of the Purkinje neurons. So Purkinje neurons receives axon terminals from climate fibers or from granules. Granule cells are activated by, right? So we have two loops here. One is called short loop, the other one is called long or deep loop cortical. So the short loop is this one, from muscle fibers and climate fibers directly to deep cerebellum. So this is the short loop. This one is excited. These two excite this. This one is excited also. It releases glutamate in the targets. Where are the targets? If this cell is located in the fastigial nucleus, they go to vestibular nucleus. Sorry, they go to reticular formation. If this one is located in the dentate nucleus, they go to thalamus and the red nucleus. Right? If it's located in the folliculonodular lobe, they go to the vestibular lobe. So they release glutamate in the target. So this is a short loop. But this one is a long loop. It goes to the cortex. It first activates granule cells. Granule cells activate Purkinje cell. But Purkinje cell is inhibited. It inhibits deep cerebellar nucleus. So the short loop is excitatory. The long loop is inhibited. The long loop inhibits deep cerebellar nucleus. So the targets are depressed, suppressed. Right? So this one is another figure from Guyton book. It's the same picture. Okay, so there are some details about the number of neurons we have. For example, we have one climbing fiber for every 5 or 10 Purkinjes. So each climbing fiber makes 300 synapses with Purkinjes. We have, for example, one muscle fiber for every, for example, 500 to 1,000 granules. Okay, so these are some details. But the general scheme is more important. Short loop.
As the number is important.
No, it's not important. I mean, these are not important for me. Okay, the number of the fibers. So again, I told you that climbing fibers active and muscle fibers activate the deep cerebellar nuclei. They go upward in the long loop, activates in the muscle fiber, activate the granule cells activate. Purkinje cell inhibits deep cerebellar nuclei. Okay. The response of Purkinje neuron to muscle fiber and climbing fiber is different. Okay, the type of action potential. Muscle fiber release glutamate onto Purkinje cell. So this is a synapse. You know, from first session you should know that neurotransmitters cause excitatory postsynaptic potential in the postsynaptic cell. Postsynaptic cell is Purkinje cell here. So we'll have EPSD. Yeah. On the top of the EPSD, I mean, if the EPSDs are enough to change the threshold, to change the potential to threshold, we'll have action potential. The type of action potential that happens in the Purkinje cell here is the standard action potential that we have. Depolarization, repolarization. Okay? Depolarization, repolarization. Well, actually, we have tightened the time here. So instead of seeing a upward phase and the downward phase, we only see one line. To pack this. Okay? So this is called simple spike. Simple spike. So simple spike means the usual action potential that we have. But if the climbing fiber activates the Purkinje cell, then the type of the action potential is different. It's like this, or like this. First, we have an action potential like this, but in the repolarization phase, we will have smaller spikes like this. We call this complex spike. So, Purkinje cell neurons may have two types of activities. Simple spike, complex spike. Simple spike in response to massive fiber excitation, complex spike in response to climbing fiber activation. Right? So they have physiological roles. We'll see. Okay. Purkinje cell inhibits deep cerebellar nucleus. The number of action potential in Purkinje cell is high, but the number of action potential in the deep cerebellar nucleus is higher. So this one tends to inhibit the deep cerebellar nucleus, but deep cerebellar nucleus is more active. So, in the resting state, we always have output signals from the deep cerebellar nuclei to the targets. Okay?
So the action potentials don't stop even if
Yeah.
that inhibition happens.
Exactly.
It's
Even though we have an inhibition from Purkinje cell,
it just gets depressed a bit
yeah,
more.
so they keep them actually at lower rates. Okay? So there is a balance between excitation and inhibition. But this balance is slightly in favor of excitation. So now let's see what is the contribution of these loops and their activity function of the motor system. Imagine that we want to do a simple movement like this. Like this, reaching. Okay? So it has a start and an end. So the end is here. Like I want to pick up this. So the start is here, end is here. Okay? So for any movement, we need activation of agonist muscles, inhibition of antagonist muscles. At the start of the movement, we need excitation of the muscle. At the end of the activity, we need breaking the movement, I mean inhibition of the muscles, right? So, what is the function of the cerebellum? The cerebellum sends some corrective signals at the start of the movement to the motor system, and then it removes the signal at the end of the movement. How? I told you that we have a short loop, a long loop. At the beginning of the movement, massive fibers are activated from the cortex, right? So they come here in the cerebellum, they activate directly the deep cerebellar nucleus. Deep cerebellar nucleus send the signals to the cortex, corticospinal tract, right? The origin of the cortex. So, at the beginning of the movement, the short loop supports excitation of the cortex. But after that, the movement starts and goes on. Meanwhile, we have activity in the long loop. Signals go upward in the cortex, which the Purkinje cells are activated. They inhibit deep cerebellar nuclei, right? So, in this time, actually, the movement has reached to its end. At the end of the movement, Purkinje cell is activated, deep cerebellar nucleus is suppressed, so the support of the cerebellum is removed. So we can say that at the beginning of a movement, the cerebellum supports the excitation of the cortex. At the end of the movement, the cerebellum inhibits the motor cortex. So this way, it can help the beginning and the end of the movement, right? So again, we have on and off signals to the muscle. The on signal is supported by the cerebellum. The off signal also is supported. The on signal is supported by the short loop. The off signal is supported by the long loop, right? Because the signs are different. Okay, so you can see that the details from pattern signal through punctile muscle fibers, cerebellum nuclei, excitation of the signal, corticospinal tract, turns at the end of the movement. Muscle fibers, second branch, granular cell, parallel fibers, Purkinje cell, they inhibit with cerebellar nuclei, so there is a turn of signal for antagonism, right? The opposite happens for antagonist muscles. Okay? So we want to talk about this for antagonist muscle. So this way we can say that Purkinje cells can support the onset and offset of muscle contraction. They also regulate the degree and timing of the support. Okay? I mean, short loop supports the onset, long loop supports the offset of a movement. But this support has a timing and has a degree. Okay, how well it can support the onset or offset. So this is something adaptable. Okay, so imagine that you want to do this movement for the first time and you are not very skillful in this. Okay, so the cerebellum tries to support the onset and offset, but there may be some mistakes. Okay, but you may need to do this movement very fast and very precise. Okay, what does it mean? Fast. It means the onset should be stronger, the offset should be also strong, and the duration between onset and offset should be shorter. Right? So, this way, I mean, the cerebellum can increase or decrease the excitation of the synapses. Which synapse? The synapse between the granular cell and Purkinje cell. If the synapse is facilitated, it means that the long loop actually can function faster. Right?
Yeah.
Onset starts,
Also,
and yeah, the action potential can go to the granular cell, from granular cell to the Purkinje cell, and here it can go faster. So the delay between the onset and offset is not short. So the action can be done faster. Sometimes we may need to put a delay between the onset and offset. So this synapse can be suppressed. So this way the long loop can function slowly, more slowly. Okay? So this way we can put a delay between the onset and offset. So the degree of the support and the timing is something regulatable. So the cerebellum can regulate this activity, and this way we can learn a motor movement. Okay? For learning this movement, climbing fiber is very important. And the complex spike has a main role. So climbing fiber can change the sensitivity of the synapse between the Purkinje cell and the granular cell. Okay? So we want to have a break.